Have you ever really thought about what's happening when you stretch a rubber band until it's about to snap? Or when you crush a soda can? Or even when an archer draws back a bow? Well, it all comes down to the physics of forces and elasticity. And today, we're going to dive right into the science of that stretch and squish. So here's our game plan. We'll kick things off with the basics of how forces change an object's shape. Then we'll look at why some things bounce back and others don't. After that, we'll get into a famous rule that governs springs, see what happens when you push that rule to its breaking point, and finally, we'll uncover the secrets of how energy gets stored up in all this.
All right, let's jump right in. First up, what is actually happening on a physical level when you apply a force and change an object's shape? I mean, this is the real question, isn't it? Why does a spring on a trampoline bounce you back up, but if you bend a paper clip too far, it just stays that way? It all boils down to how different materials respond to being pushed and pulled around. Now, here's a key idea you might not have thought about. You can't actually change an object's shape with just one single force. To bend a bow, you're pulling the string one way while the bow resists. To stretch a band, you're pulling both ends apart. And to crush a can, you're squeezing it from opposite sides. It always takes more than one force to get the job done. And you know, there's a scientific term for all this bending, stretching, and squashing. It's called distortion. It's just the official word for any change in shape or size that happens because forces were applied to it. Okay, so once an object gets distorted, it can really only go down one of two paths. This is where we get into that crucial difference between things that bounce back and things that, well, don't. First, you've got elastic distortion. The rubber band is the perfect example, right? You stretch it out, you let go, and boom, it snaps right back to how it was before. That ability to return to its original form is what makes something elastic. On the flip side of that, you have inelastic distortion. And this time, think about stomping on an empty soda can. It's not bouncing back from that, is it? The change is permanent. The forces have basically pushed it beyond its point of no return. So, now that we're clear on elastic objects, the ones that bounce back, let's check out the really cool and elegant rule that actually predicts exactly how they stretch. And, you know, this is what makes things like springs so incredibly useful for engineers and designers. Their behavior isn't random at all. It follows a super clear, simple, and predictable principle. And that principle is called Hooke's law. So what on earth does directly proportional actually mean? Honestly, it's really simple. If you double the force you're pulling with, you get double the stretch. Triple the force, you get triple the stretch. It's this perfect straight line relationship. Let's just quickly break down that little formula. F is pretty straightforward. That's the force you're applying, and we measure it in newtons. X is the extension, basically how much the thing stretches, and we measure that in meters. And then there's K. That's the special sauce. So this K, the spring constant, is basically a number that tells you how stiff an object is. Every spring has its own unique K value. Think about a heavy-duty spring in a car's suspension. That's going to have a really, really high K. It takes a ton of force to compress it even a little. But a slinky, that's got a super low K value. It stretches with almost no effort at all. But here's the catch, and this is so important. That beautiful, simple rule, Hooke's law, it doesn't last forever. Every single elastic object has a point where the rules change. Let's see what happens when you push it just a little too far. So you can pull on a spring and it follows Hooke's law perfectly. It's predictable, it's reliable, but only up to a point. If you keep pulling and pulling, you will eventually hit a moment where that nice, neat relationship just completely breaks down. And hey, don't just take my word for it. Check out this real-world data. We apply a force of about 1 newton, and the spring extends 30 millimeters. We double that force to about 2 newtons, and look at that. The extension almost perfectly doubles to 61 millimeters. That is Hooke's law in action, right there. And that tipping point we've been talking about? It has a name, the limit of proportionality. It's the exact point on the graph where that lovely, predictable relationship between force and extension just stops. Any more force beyond this point, and the object goes totally off script. So let's just recap that. Below this limit, you're in the linear region. Everything is fine, Hooke's law works, and the object is elastic. It'll snap back. But the second you cross that line, you enter the nonlinear region. The rules break down and you start doing permanent damage. The object is now inelastic. And all of this brings us to the final and maybe the coolest part of the puzzle, the energy.
Because when you're pulling on that spring, you're not just changing its shape, you're literally loading it up with potential.
Seriously, think about it for a second. It takes work. It takes energy from your muscles to stretch that spring. But that energy can't just disappear into thin air. Physics doesn't work that way. So, where does it go?
It gets stored right inside the material itself as something called elastic potential energy. As long as you don't stretch it past that limit of proportionality, all of the work you did pulling on it is perfectly saved up, just waiting to be released. So, how much energy are we actually talking about? Well, for a spring with a stiffness, a K value of 3 newtons per meter, if you stretch it by half a meter, you end up storing exactly 0.375 joules of energy. Pretty specific, right? So how on earth do we get that number?
Well, we use this powerful little formula right here. The elastic potential energy, EE, is equal to 1/2 times the spring constant K times the extension x squared. First, you've got to make sure your units are right, so we convert 50 centimeters to 0.5 meters. Then you just plug the numbers in, half of 3 times 0.5 squared. Run the calculation, and there you have it, 0.375 joules.
So now that you know the secret, you'll start seeing it everywhere. It's in the clicky spring in your pen, the shock absorbers in a car, the bounce in the soles of your running shoes. This principle is all around us. So the next time you stretch or squash something, just think about that stored energy, all that hidden potential just waiting to spring into action.